All right, hi guys, we're back again for lesson 1.3 where we're going to get into piecewise defined functions. And much like the title says, these are functions that are kind of chunked out into pieces instead of being like one smooth continuous curve or one smooth continuous line. So we're going to start off with an example, like a context example. So it says Alani has a summer job as a lifeguard. She makes $8 an hour for up to 40 hours a week. If she works more than 40 hours a week, she makes 1.5 times her hourly pay. Graph and write a function that shows her weekly earnings, right? So basically she gets overtime. She works more than 40 hours, she gets overtime pay. She gets paid a little bit more. So if we don't have Desmos, what we would do is start with making a table so we can get some points. So let's do that. If I plug in 20, she works 20 hours, she's getting $8 an hour because it's less than 40, right? So I am just figuring out here what 20, oops, sorry for shaking the table, 20 times 8 is, and that is just $160, okay, for that week. If she works 25 hours, 25 times $8 an hour, that gives me $200 for the week. She works 30 hours, 30 times 8 gives me $240 for the week. 35 gives me $280. And then if she works full time, all 40 hours, that's $320 a week, right? Now here at 45 is where it changes a little because for the first 40 hours, she makes $320. But for those extra 5 hours, she makes 5. So those 5 hours, she makes $8 an hour, but 1.5 times that, right? So that ends up being, for 45 hours, $380. Squeezing it in there so hopefully you can see it. If she works 50, using that same equation, that would be $440. And 55 is 500. So I'm not writing this out, but it would be the same thing. It would be the original 320 plus, this would be 10 extra hours times 8 times 1.5. And that's how you get that 440. Okay? So if you need to write that down, if you want to see that, it's like this. Oops. 10 extra hours, $8 per hour, and 1.5 times that. That's how you get that for 50. And 55. That's 15 extra hours at $8 an hour times 1.5 times. Okay, so that's how we're getting those. So now let's just plot them. Okay, so if she works, I'm going to go ahead and I know that I'm going to plot this till 55. So let's just go by tens. 10, 20, 30, 40, 50, 60. My pay is going from 0 to 500-ish, so let's just go by 1, 2, 3. Let's just go by hundreds here. 100, 200, 300, 400, 500. Okay, so that's dollars. So I'm going to use a different color here for graphing. So if she works 0 hours, $0. If she works 20 hours, she's at 160. It's a little bit more than half, so here. If she works 25 hours, she's at 200. She works 30 hours, she's at 240, so a little less than half, so maybe here. 35 is 280. 40 is 320, so a little bit more right here, right? So this is really ideally, if I had a graph paper and did a great job, should be all along this line. So I'm going to pretend, because it's a linear function, right? It's always increasing by $8 every hour. Okay, but then something happens after 40 hours, right? So I'm going to use a different color just to show that. At 50, she's at 440, so something maybe here. And at 55, she's at 500, so maybe here, right? And it connects here. So it's still a linear function because it's growing by a constant rate of 1.5, It's just the slope is getting a little steeper because she gets paid more for the every hour after 40. So this is what we call a piecewise function, because the rule for this part of the function when x is less than 40 is different from the rule for this part of the function when x is greater than 40. So this is how that function looks, and then if I were to write it, it would be, let's just call it pay. P of x equals, okay, I'm going to write in red what that function is. So the way you would find every point on this function would be just to take the number of hours worked, which is x, and multiply it by 8. And that would be true for 0 to 40, right? That's the rule or the equation expression to finding all of the points on the red part of the piecewise function. And then the blue part, right? How do we find this? Okay, so there's kind of two ways to do that, right? So how are we going to write this into a function? So we could think of what is the new pay. So we know that the new hourly pay is 1.5 times 8. Well, what's 1.5 times 8? It's going to be 12. So really, every hour she works after 40, she makes $12 an hour, right? So that's $12 times every hour she worked, plus, where do we always start? Plus, where did she start here? She started with, at 40 hours, being at 320. And that's how you could find every point here. Except we'd have to differentiate here. What is x, right? Because we're changing x. We're actually going to have to change this. Let me erase this. I'm going to write that here. 12x plus 320. So that would give us her total amount she makes. But we've changed x here because now our x depends on every hour after 40. So what could we put here so this is an accurate representation, like if I wanted to put 45 in, right? So the way I do that is kind of what we have here. We know that her pay is 8 times 40 for those first 40 hours, plus the $12 she makes after every 40 hours. And then it's going to be, to get this real value of x, we have to take the number of hours and take away the original 40, because we just want the extra hours past 40. So then when I work that out, it ends up being 8 times 4 is 320 plus 12x minus 40 times 12 is 480. Then we simplify that more. Can combine 320 minus 480 and we get the linear equation 12x minus 160. So this ends up being 12x minus 160 when x is greater than 40. So this is our piecewise function. And I realized you couldn't see that bottom, so hopefully you can see it now, right? So my original thought of just plugging this in here didn't make sense because I had to adjust to make this x for every hour over 40. You couldn't just use the number of hours, okay? So hopefully that context makes a little sense. Let's try some more piecewise functions. Okay, so this one we're giving a graph and we have to plot it. So that is not too tricky. Let me make sure it's focused here. Okay, there we go. So 4x plus 1 when x is between -10 and -2. It's allowed to be -10, not allowed to be -2. So let's just make this part purple. Okay, so let's plug in some numbers here. I'm going to just come over here. X and then 4x plus 11. Okay, so 4x plus 11. If I'm just going to plug in, let's plug in -10. Let's plug in -5. Okay, let's see where that gets us. So 4 times negative 10 plus 11, that's negative 40 plus 11, which is 29, negative 29. Sorry guys, I'm dealing with other tech here on the side. All right, now let's plug in negative 5. 4 times negative 5 plus 11 is negative 20 plus 11, which is negative 9. Okay, so let's just plot those, our first part. So I don't even, 1, 2, 3, 4, 5, 6, 7, 8, 9. I made a bad choice of picking 10 when it's not even there on my graph. So let me just pick another one. Let me pick negative 8. 32 take away is 21. Okay, so that's already, I can see like this is going to end up being like down here. Let's just call this negative 8, negative 21, and then it's just going down, right? If there was a 10, it would keep going down. And at negative 5, it's negative 9, so that's actually on the graph here. 1, 2, 3, 4, 5, yep. So I can kind of see that this line, and where would it be if it was at, if it could be negative 2? We know it can't be that, it's going to be open there, which is 3, right? So it's going up to negative 2, 3, but I know it's an open circle, so I'm going to just use my little post-it here and kind of connect that up. So here's an open circle. Okay, so that's the purple part of the line. Okay, now x squared plus 1 between these two. Let's make that red. And that one, just do negative 2, 0, and 2. It's allowed to be negative 2 and 2. So those are going to be where it's filled in. And that's going to be x squared plus 1. So negative 2 squared plus 1 is 5, 1, 5, right? So we're really going at negative 2 to 5. I make a mistake here, negative 8. Yeah, so here it is 5, negative 2, and 1, 2, 3, 4, 5 here, to 2, 5, and 0, 1. Sorry, you're seeing my head in there. Right, so there's that parabola. So it's like this, right? And then these are both closed dots because these are less than equal to, greater than equal to, or less than equal to, both of them, right? Okay, and then now we're continuing on. Oh, I see where my mistake is. I'm looking at this, I'm like, why is this wrong? But we're gonna leave it. Okay, so now let's do this last function in blue. X plus 1 for 2, between 2 and 10. So let's do x plus 1 between 2 and 10. So we know we're going to connect 2. Let's just do 5 and 10. 2 plus 1, 3. 5 plus 1, 6. 10 plus 1, 11. That's easy. So 2, we're at 3. Open circle, because we're not allowed to be that. 5, we're at 6. 1, 2, 3, 4, 5. Get my head in there, sorry. It's hard for me to see. And 10, which is over here, we'd be up at 11 somewhere. So our line, it's another linear function, right? The slope of 1, something like that. So that's our piecewise function. It looks a little weird. I realize I copied the example wrong. That's why this middle one's weird. But this is correct for what we have up here. So piecewise function, it's different functions kind of combined together. It's still a function because for every y value, or for every x value, there's only one y value, right? So now what if we have to find the domain and range? Is the domain restricted? No, the domain in between these, it can be all of these points, right? Even though there's an open hole here, it's filled in there, and same there. But our domain is restricted by what's up here. So we've gone from all values from negative 10 to 10. So if I do interval notation, my domain is going to be, we're allowed to be negative 10, so that's a bracket. And we're also allowed to be 10, so that's a bracket. And what's my range? So now I'm looking at my graph. I start all the way down from negative 10, the value was negative 29. And we can be negative 29, so we're going to include that. All the way up to what's my greatest value? My greatest value happens to occur at x equals 10, and that's 11. So we're just reading the domain and range off the graph. You have to be careful though, because your maximum and minimum points don't always occur at your endpoints. I just have the graph here so I can check it. Okay? One more example with piecewise functions. Sometimes you'll be given the graph and you have to write the rule, kind of like we did for the first one. So we are going to write the rule for this piecewise function. Let's talk about segment 1, or segment A, this purple section, right? So the domain here is x is allowed to be starting all the way from, what is this? Negative 1? Yeah. Negative 1, 9. So from, we can do it like this. So x is greater than negative 1 all the way to where x is 1, right? But it's an open circle, so I know that it's just x is less than 1. What is the function for this piece here? Well, I have to zoom in really closely. Let me zoom in for you guys. Let's find, it's a linear function, so let's find the slope. What's the slope of this line? I'll just do it on the side here. y2 minus y1 over x2 minus x1 is slope is 4. So if I'm remembering slope intercept form, it's going to be 4x plus, what's the y-intercept here? So I actually need to change that. The y-intercept is 1, 2, 3, 4, 5. So 4x minus 5. So that is the function in between these two intervals, okay? 4x minus 5. All right, now let's deal with B. Make that blue. Let's just call this thing f of x2. So right here I can write f of x equals, okay, so we're gonna have 3 parts, right? Okay, this blue part, section B. Section B, it starts off from x equals 1 to x equals 5. So from 1 to 5. And they're both closed circles, so I know that's why I'm using the less than equal to symbol, okay? So it starts off, it's also a line. So what's the slope of this line? I'm gonna do it in blue down here. Slope is 8 minus 4, y2 minus y1 over, let me zoom out so you can see what I'm doing, over 5 minus 1, that's 4 over 4, which is 1. Nice easy slope of 1. So it's, the slope is 1x, or x. Remember, I'm just using slope intercept form because it's easier for me. Okay, and then what is my y-intercept? So if I kept going here, just imagine this thing kept going, the y-intercept would be 0, 3. So it would occur at positive 3. So that's the second part of the function. And then part C, this red part, it's a constant function, so it's always equal to 8 no matter where it is. So that part is pretty easy because we can just write that the function is equal to 8. When is it equal to 8? When x is less than or equal to 8, and also less than, and then greater than or equal to 5. So this right here is our rule for the piecewise function. Okay, more practice, and think this isn't too bad. It's just learning how to read graphs and write the functions you see from them, okay? See you next time.